Our last topic this week is solving nonlinear systems. I'm going to go through 3 examples with you and also discuss how to check these on your calculator. We will solve all of them algebraically. Sometimes you will be asked to solve them with your calculator, so I'll show you both. But today we'll focus on the algebra. So here I have x squared plus x minus y equals negative 1, and x plus y equals 4. So when I look at those equations, I see a parabola and a line. So I know that they might intersect in 2 places, 1 place, or not at all, if I were to graph them and when I graph them to check. But to solve these algebraically, there are a couple of different things we could do. I think the way I would approach this one is to take my second equation and solve for y, and then substitute that expression into the first equation. So that's what I'm going to do. I'm going to take x plus y equals 4 and get y alone. So y equals 4 minus x. Now I can take that expression, 4 minus x, which I know is equal to y, and substitute it into the other equation. So now I have x squared plus x minus y, but y is 4 minus x equals negative 1. Now I'm down to one equation. So let's clean it up. I have x squared plus x minus 4 plus x equals negative 1. Combine like terms, x squared plus 2x minus 4 equals negative 1, and set it equal to 0. I'll add 1 to both sides. X squared plus 2x minus 3 equals 0. So now we're back to a basic quadratic to solve. Our choices are factoring, completing the square, or the quadratic formula. I'm going to try to factor this. Can I come up with 2 numbers that multiply to negative 3 and add up to positive 2? Well, 3 is 3 times 1. Those are my only choices. If I need them to multiply to a negative, the signs have to be opposite. And if I need them to add to a positive, the larger number has to get the positive sign. So positive 3 and negative 1 will give me a product of negative 3 and a sum of 2. Because a is 1, I can put those numbers in my factors immediately. So my factors are x plus 3 and x minus 1. Setting those factors equal to 0, x is negative 3 and x is 1. So those are the 2 x values to my solution. It's a system, so I need both x and y. So I'll substitute into the simplest original equation to find my y value. So x plus y equals 4. Well, now I know that x is negative 3. So negative 3 plus y equals 4. Getting y alone, y is equal to 7. So negative 3, 7 is one of my solutions. I'll do the same for 1. X plus y equals 4. X is 1 plus y equals 4. Y is 3. So my other solution is 1, 3. Remember, when you're solving a system, you want to solve for all possible values, and you must find x and y, because they're points of intersection. So speaking of points of intersection, let's graph both of these. I've already gotten the linear function alone, y equals 4 minus x, so that's in good graphing form. I'll need to do the same thing with the quadratic, the parabola. So I need to get y alone. It needs to be positive y. So I'm going to add y to both sides, and then add 1 to both sides to rearrange. So I'll have y equals x squared plus x plus 1. Adding y to both sides, and then adding 1 back to the other side, and then rearranging them on opposite sides of the equal. So now I can enter these into my calculator and check my points of intersection. Do a quick review of that. So on a graph scratch pad, or just a graphs page, we'll type our 2 functions, 4 minus x, for the linear function. I shouldn't be surprised to see a line, y-intercept of 4 and a negative 1 slope. And I need to get my other equation in, x squared plus x plus 1. And I should see a parabola that opens upward with a y-intercept of 1. And there it is. Now what I really care about here are my points of intersection. You may want to adjust your window a little so you can see some more of your graph up there. And that's a little bit better. So I need 2 points of intersection. So remember, we menu, analyze graph, intersection, you need to go to the left of one of your points of intersection. So since I'm here, I'll choose my rightmost point as my lower bound, and then my upper bound. There's an intersection point 1, 3. Let's check the other. Again, menu, analyze, intersection. Need to go to the left of the other intersection point, and then over to the right of it, negative 3, 7 is the other points of intersection. Remember also, real quickly, that if you had looked at the table of values, you could have checked that those points were solutions. There's 1, 3 in my table, and there's negative 3, 7. That doesn't necessarily show you the point of intersection until you scroll over and see both functions have a y value of 7. So when x is negative 3, both y's are 7, and when x is 1, both y's are 3. So that's another nice check of your algebra. Okay, let's do another. We're going to solve y equals x squared minus 2x minus 1 and y equals negative 2x minus 1. Okay, so again, I have a parabola and a line, and I'm looking for points of intersection. But we'll solve this algebraically. Well, because y is equal to two different expressions, those expressions must also be equal to each other. So that's what I'll do, is set them equal. So x squared minus 2x minus 1 must equal negative 2x minus 1. As always, we want to set this equal to 0. So I'll add 2x and add 1 to both sides. And when I do that, I'm left with x squared equals 0. We undo squaring by square rooting. The square root of 0 is 0. So here it seems that we only have one point of intersection, because I could plus or minus the square root of 0, but that's 0 both times. Let's substitute in and find our corresponding y value. So y equals negative 2x minus 1. Replace x with 0. Y equals 0 minus 1, which is negative 1. So it would appear that this system, this parabola and line, only have one point of intersection, and that it's 0, negative 1. And what I'll do is check that on my Inspire again. Go to Menu, Actions, delete all to start fresh on my Scratchpad. If we were in a document, you could just add a new graph page. So my first graph is x squared minus 2x minus 1. There's the parabola. And my next graph is negative 2x minus 1. There. So it would appear, again, that there's only one point of intersection. Let's analyze that. Menu, Analyze, Intersection. Lower bound to the left, upper bound to the right. And there it is again, 0, negative 1. Now for a quick review, whenever we have a line touching something in just one place, exactly one place, almost kind of skimming it, and only having one point of intersection, that line is called tangent to the graph. So we would say that the line negative 2x minus 1 is tangent to the parabola x squared minus 2x minus 1. We talked about tangents in geometry class, and we'll do much more with tangents this year. So let's do one more. We need to solve 2x squared minus 5x minus y equals negative 2, and x squared plus 2x plus y equals 0. So here I have two parabolas, and I'm curious about what their points of intersection are. We could solve for y in both cases and set those expressions equal to each other, but I do want to remind you that elimination will also work even when I have nonlinear systems as a way of solving. So right away I notice that I have a negative y and a positive y. If I add these equations together, those y's will be eliminated, just like when we solve linear systems or 3 by 3 systems. So let's do that so you can see that that will work as well. So I'm going to add these equations, and I get 3x squared minus 3x. My y's are eliminated, and that equals negative 2. So I'll set this equal to 0 because it's quadratic. 3x squared minus 3x plus 2 equals 0. that's a great solution to that quadratic. However, with a system, when we graph, we're only looking for real solutions. We can only graph real numbers. And so it would appear that there are no points of intersection of these two parabolas because I have this imaginary root. Again, let's check it on our calculators to be sure. Okay, so in this first equation, I need to solve for y. So I'm going to add y to this side and add 2 to the other side to get y alone. So y will equal 2x squared minus 5x plus 2. Here to get y alone, I need to subtract x squared and subtract 2x to move those away from the positive y. So y equals negative x squared minus 2x. So here I have a happy parabola, it's a little skinny with a y-intercept of 2. Here I have a sad parabola, normal width with a y-intercept of 0. Let's see if they intersect, or if our algebra is bad. First graph, once I've got y alone, is 2x squared minus 5x plus 2. And the second graph is negative x squared minus 2x. And we can see, if I go menu, window, standard, is probably good. That's better. I can see that while they come close to each other, there are no points of intersection of these two graphs. And so my algebra was right and there was no real solution. If you tried, I'm curious, to analyze this graph with intersection points, you see we go lower bound and upper bound, and they tell us that there are no intersections found within those boundaries because there are no intersection points at all. Okay, so to summarize linear systems, we're really looking for points of intersection, but we'll do this algebraically. So if you have a parabola and a line, you could have 2 points of intersection, you could have 1 point of intersection, or no points of intersection. And same with 2 parabolas. You could have 2 points of intersection, 1, or like we just saw, none. And don't forget, we'll talk more in class about other non-quadratics, like circles. We could have 2 points with a line. We could have 4 points with a parabola. And there are lots of different non-linear systems we can solve. We'll solve them algebraically, unless we're told to graph, but we can always check with our graphs. That's it. Have a great night.